So when I mix together orbitals that are, the lines come together like this, they kind of meet edge on. Here's the edge. The edges are touching each other, right? If this is the tip, these are the tips, and these are the edges. The edges are meeting head on like this. So when these two orbitals meet like that, then let me draw them a little bit closer here. Didn't work as well as I wanted. Let me draw them a little bit bigger and then closer. You can see that when I meet two of these orbitals really close, they're going to have overlap, but they're going to have overlap, a little bit of overlap right here where these two bulbous parts bump into each other, and a little bit of overlap down here where these two bulbous parts bump into each other as they get closer and closer, right? So if these are going to constructively interfere, then they're going to get bigger. So then that shape kind of looks like this. The part where those orbitals overlap gets bigger and it joins. And so I make one big orbital like this. These two get stuck together and it makes this big orbital like this. This is called a pi bond. A pi bond happens when two orbitals meet edge on like this. This down here, I have those same two orbitals. I can imagine those same two orbitals, but instead of them meeting edge on, now they're going to meet head on. Right? So if I bring this one and this one close together, it's this part right here that overlaps. So this part right here is going to get bigger. Only one place. Here there's two places that overlap that get bigger in a pi bond. In the sigma bond, there's only one spot that overlaps. And so that part's going to get bigger, and a sigma bond looks like this. So a pi bond is where the two orbitals meet edge on, and a sigma bond is where the two orbitals meet head on. All right, so we have now, let's look at this molecule. If I gave you CH2O, the formula, we've now come a long way in the last couple of chapters. You can draw C and tell me that it has 4 valence electrons and draw the Lewis structure for C. And you can draw the H's, right? I have an H here, I have an H here, and then we can move this out of the way. CH2O. I can draw an O up here, and I know that O has 6 valence electrons. There's the 6 valence electrons for O. So then I join them together. There's a bond, there's a bond, there's a bond, and this guy over here is going to make a double bond to oxygen. So then I would get this structure right here, right? So we know now, you do too, how to take this formula and draw the Lewis structure, join the valence electrons to make this structure here, right? Carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Hydrogen has 2, it can only hold 2. So here's my complete Lewis structure. Now I can take that one step further and say, this has 1, 2, 3 electron groups around it. 3 electron groups. Remember, a double bond and a triple bond still count as 1. So 1, 2, 3. So then I can go back to my table and say, okay, this has 3 groups, 3 bonds, and 0 lone pairs. 3 bonds and 0 lone pairs is called trigonal planar electron geometry. And since there's 0 lone pairs, it's also called trigonal planar molecular geometry. And the bond angles are 120 degrees. So we can go back to our picture here. And we can say this is called trigonal planar. And these bond angles are all 100, let me try that in a different color. These bond angles are all 120 degrees. Right? And now we can look at the electronegativity. The electronegativity between C and H, that difference is 0.4. So this is a non-polar bond. And here, the same, 0.4, non-polar bond. The difference between carbon and oxygen is 1, an electronegativity difference of 1.0. So this is a polar bond. CO is a polar bond. So do those dipole moments cancel out? Well, no, because I only have one. If this is the only polar bond in the molecule, then it can't cancel these because these aren't dipole moments. These are non-polar bonds. So what that means is that this is a polar molecule. It has one polar bond, and it is also a polar molecule. All right, so now, finally, now we're going to add this last piece of information. So this looks really complicated, but we've already talked about most of this stuff. We already know what most of this is over here. So now let's try to explain what we're seeing here in terms of what we already know, because we've already done all of this. So there's a bond between C and H. Here's that bond between C and H. We drew it like this. We drew it as a stick. But we also, up here, we drew it like this and said, well, carbon brought one electron and hydrogen brought one electron, right? So we said there's one electron from carbon, one electron from hydrogen. That's what this is saying too. This up arrow is one electron from hydrogen. It has an up spin. And here's an electron from carbon that has a down spin. So there's two electrons in this bond. We're saying the same thing. We're saying now that hydrogen, when I draw this hydrogen atom, it really has this sphere around it, right? And that's where the electron is. And that sphere around hydrogen is in an orbital called 1s. So this orbital right here where the electron is in hydrogen is a 1s orbital. I know that from the electron configuration of hydrogen. This electron on carbon, because I know that this carbon is making 3 bonds, 1, 2, 3 electron groups, then I know that I need this to be sp2 hybridized. And I can also see that because the bond angle is 120 degrees, then that also tells me that this is sp2 hybridized. So if I know what the geometry is, because I looked it up on a table, then I also know what the hybridization is, because the geometry that gives me 120 degree bond angles is also the hybridization that gives me 120 degree bond angles. sp2 and trigonal planar are the same. There are two ways of saying the same thing. So if I know that this is trigonal planar, so if I know that this is trigonal planar and I know that the bond angles are 120 degrees, then I know that sp2 hybridization also gives me bond angles of 120 degrees because those 3 sp2 orbitals can separate by 120 degrees, just like trigonal planar geometry. So what I'm looking at here is this: a carbon atom has 3 sp2 electrons. 1, 2, 3. Hydrogen atoms, here's a hydrogen atom, here's a hydrogen atom, hydrogen, hydrogen. These hydrogen electrons are in a 1s orbital, 1s. And their electrons, in order to go into an orbital together, they have to be spin paired. So these will be down spin. Spin up on carbon, spin down on hydrogen. So this bond right here between carbon and hydrogen, that's this bond right here. So now I can go one step further on my Lewis structure. Now I know all this stuff about it. I know the angles, I know whether it's polar, I know the geometry, and now I can go one step further with what I'm learning in this chapter, and I can say this bond is a 1s sp2 bond, because the hydrogen's bringing a 1s and the carbon's bringing an sp2 electron. So this bond right here is a 1s sp2 bond. What about the bond between carbon and oxygen? Well, if we draw the oxygen up here, it's a little bit too big. Oxygen has one. I'm going to get rid of some of our stuff around here. Let's focus on oxygen here now. Oxygen has 1, 2, 3 electron groups around it, right? 1 is a bond, and 2 of them are lone pairs. So if oxygen has 3 electron groups around it, then how far apart are those electrons going to be able to spread out? Well, 3 groups, the furthest apart that they can get is 120 degrees, just like down here on the carbon. So this oxygen kind of looks like this. These are the lone pair electrons. Has 2 lone pairs, right? 2 lone pairs. 1 lone pair is up here in this sp2 orbital. 1 lone pair is here in this sp2 orbital. And then carbon also, or oxygen also has this unpaired electron. And one of these unpaired electrons on oxygen is going to pair up with this unpaired electron on carbon. So this one spin up in an sp2 orbital. And oxygen is spin down in an sp2 orbital. And these are just lone pairs here. So I can take what I know about Lewis structures and take what I know about the electron configuration that we learned in chapter 6. And so basically what we're looking at here in chapter 8, this is chapter 6 plus chapter 7. I'm taking the stuff I know about s orbitals and p orbitals and spin up and spin down from electron configurations in chapter 6. And I'm taking what I know about Lewis structures, where I can show bonds and angles and single bonds and double bonds, and I'm combining them into this one picture of what a molecule looks like. So this is molecular orbital theory, this is actually valence bond theory that we're looking at here. And valence bond theory talks about where the electrons, what orbital the electrons are in, and how they overlap like this. Well, this orbital here overlaps with this orbital here, so the electrons spend their time in the middle, and that's what creates the bond between the carbon and the oxygen. Finally, if I have one s orbital and one p orbital, and I do the same kind of mixing, the same hybridization that we've been talking about, 2 atomic orbitals in gives me 2 molecular orbitals out, 2 hybrid orbitals out. So when I put this one and overlap it on this, how far apart can 2 electron groups get from each other? 180 degrees. So sp3 is tetrahedral geometry, because there's 4 electron groups. sp2 is trigonal planar geometry, because there's 2 electron groups. Go back to my chart here. Right, so the first one we started with were these. We call these sp3 hybridized, because there's 4 electron groups. When there's 3 electron groups, those are sp2 hybridized. And when there's only 2 electron groups, that's sp. And how can you keep track of this? Well, 1s plus 3p equals 4 groups. Right, and that's what sp3 means. 1s, 3p's is 4 groups altogether, 4. 1s plus 2 p's, 1s plus 2 p's equals 3 groups. Right? And 3 groups is going to be 120 degrees apart. And when I have 2 groups, 1s and 1p, then I get linear geometry, and those are going to be 180 degrees apart. So again, this hybridization is just another way of describing what we already looked at in the last chapter. So with sp, I'm just mixing 1s and 1p. When I mix them together, I get 2 hybrid orbitals that are right in the middle, that are halfway in between the s and the p orbitals that I mixed. And I left these 2 unhybridized, so they remain over here unhybridized, higher energy. So in an sp geometry, I have 2 sp hybrid orbitals and 2 unhybridized p orbitals. So this is what that structure would look like. I have the 2, each carbon has an sp orbital. These purple ones are sp, 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 and this carbon has 2 sp orbitals, sp, sp. This hydrogen is 1s, this hydrogen is 1s, and these red orbitals on carbon, these are the unhybridized p orbitals. Here's one unhybridized p orbital, and here's the second unhybridized p orbital. So this is 2p and 2p. So this bond in the middle is called a sigma bond. You can see that because this orbital and this orbital are meeting head-on right here. Their heads are pointing at each other. That's called a sigma bond. But this orbital is meeting edge-on with this orbital, right? Their edges are meeting. So this is a pi bond. And it's overlaid by this one here because remember, p orbitals are perpendicular to each other. So I've also got a set of p orbitals kind of on the z-axis here, right? These are kind of perpendicular to these that are going up and down. And when these that are on the z-axis here, when these overlap, they're also overlapping edge-on. So that's another pi bond. So I have one pi bond from the overlap of the orbitals on this axis, on the vertical axis, and I have one pi bond from the overlap of the 2p orbitals on these axes, on the z-axis here. So overall, how many bonds do we have? A triple bond has 1 sigma bond and 2 pi bonds. Just like a double bond has 1 sigma bond and 1 pi bond.